Hello and welcome. In this video, we are going to measure the phase lag of this RC circuit. So last we learned that inductors had a phase lead, meaning that the inductors would push back on our voltage sources. We got to actually protect against that a little bit, but capacitors do the opposite. They pull on our voltage source, which means that we'll end up with a phase lag from our capacitor response. So we're going to measure that using an oscilloscope. The oscilloscope can be found on the sidebar, fourth one down, or in the simulate instruments, fourth one down there, as well as our oscilloscope. This is the 2-channel oscilloscope, which we need to measure across our voltage source and across our capacitor here. So we can place the positive lead of our channel A across the top of our voltage source, and then the negative side goes to ground, or the negative side of our voltage source here, and that can be anywhere on this bottom line here. So we can place it right there. The positive side of our channel B needs to go around our capacitor, which means that we can place it right up here on this elbow here, and that's going to be the top side of that capacitor. And the negative side gets to go to the bottom side, which is also the same exact location that we just placed our negative terminal of channel A. So from here, we can click on the channel B positive lead, right click and segment color, and that is going to allow us to change the color of that wire so that we can visually see the difference between these two circuits here. So double click on our oscilloscope. We're given a couple of things already here. We are given that the XC value is 159 ohms. That's calculated based on this kilo-ohm hertz, or the kilohertz frequency over here. And so we can use that value as what we expect our capacitor to do in terms of its resistance. And so let's hit play on this and we'll see what our waveforms show. It's really small. It's because our peak volts are pretty small here, so we just need to zoom in on it. And we'll first zoom in on our waveform to see it stretch a little bit, and then on channel A, our scale can go down until we stretch up our signal high enough to meet our needs here. See, that's too far. It goes off the chart, so we'll go down 1. And then we'll do the same thing for channel B here. We'll scale it down until it reaches about the same height as that one. And that's probably as close as we're going to get without it scaling off the chart. So we'll leave it right there. We can scale down our time base a few more clicks here to get it nice and smooth signal. And then we can come back, and we want to get 2 full waveforms in our view. That's another click here. And so now that's what we see here. We see the red waveform is coming in first, right? In terms of time, we see the red comes first, and it comes up, hits its peak, and starts to fall down before we even get to the peak of the blue one, which means that the red one is in front of the blue signal here, and that blue signal is our capacitor lead. And that means that the capacitor is lagging in terms of voltage and current behind the original source here. Okay, so we are going to measure the peak voltage first, and that is going to be our period. So we're going to go right-click on the yellow marker, next maximum, and that is at the top peak of that red signal, and we'll grab that blue one, and then right-click, go to next maximum, and those are the 2 top peaks, and that gives us our frequency in terms of time. So that is our period, and we'll write that down. We'll say that T is equal to 1 millisecond. So T equals 1 millisecond. Make sure your frequencies are what they requested it to be. After that, we want to measure the difference between those 2 signals, and we got to get the ones that are close together. So we see that the red waveform rises and falls, and then that right there is where the blue waveform starts to rise. So we want to compare these 2 peaks here. So to do that, we want to compare them on that white line, because that's going to give us the most accurate reading due to sampling of our oscilloscope. So we'll right-click the first meter here and set it backwards to 0. And that's going to put it right back on that white line right there, right when that red line crosses that white axis line. And then we'll grab the other probe line here, and we see that it's still following that red signal. So we can't get it to the 0 crossing of the blue line until we swap it to the other terminal there. So we can do that by double-clicking on that blue line, or you can right-click, select trace, and go down to channel B. And we'll OK. And so now we see that little ball is up on that blue line, and it's tracing that blue line now. So now we can right-click the yellow marker and go backwards to the next Y value of 0. And that will be on that axis line. And we know that this red one over here, the axis line for this red signal is right where this blue line is. And so that's where we want it. And so those are the 2 values that we're going to compare. And this gives us a 224.9, so we can round that up, 225 microseconds. And that's our difference in time. The difference in time is equal to 225 microseconds. Since our original frequency here is in milliseconds, I'm going to move this time value down. T is equal to, and instead of microseconds, I want it in milliseconds. And so I'm just going to move it back 1, 2, 3 locations and put a period or a decimal point right in front. So it's 0.225 milliseconds. Okay, so those are the 2 values we're going to use. I'm going to erase the other one here so that we don't get confused with it. And we can plug that into our Desmos over here. We can say that we have the change in time on top, so 0.225, divided by the change or the total period on the bottom, and that's only 1 for us because they're both in milliseconds, they're going to cancel out. And then we can multiply that by the number of degrees that we have in our circle, which is 360. That gives us a phase angle of 81. Right? And that's what we expected. 81 degrees is going to be the phase difference between these two components. So this is actually a high-pass filter, or a low-pass filter, right? Because our frequency is going to come up here through the through the resistor up here, and everything is going to be allowed through this resistor, but the capacitor is going to dump anything that is a high frequency across it to ground. And so we are going to lose all high frequencies to ground, right? Which means that the capacitor at the same time is going to stop any low frequencies from crossing it, and all low frequencies will be available across the resistor. And so we'll pull that out and we'll put that to a speaker, right? Or a digital waveform, something that we need to filter with. And this is going to be a low pass frequency. And so we'll be able to allow slow voice signals through, and we'll be able to eliminate any high frequencies across our capacitor down to ground. Okay, let us know if you have any other questions.